So thanks to you all for coming, and thanks to the PEPM PC and chairs for inviting me. I want to accomplish a few things with this talk. So I want to tell you a little bit about the technical details related to network verification that my group has been working on for the past few years. But I also want to try and give a broader perspective on how ideas from PEPM and POPL can be applied to networking. I think it's a really interesting time, and there's a chance for our community to really have an impact. So traditionally, networks have not been sort of the most fertile field for formal verification. And if you go back and kind of look at some of the original texts that were written when the internet emerged, you can start to see the reasons why. So this is a very famous paper in the networking community written by David Clark. He's one of the sort of main architects of the internet's design. It's a beautiful paper. It makes a wonderful set of design decisions and discusses trade-offs, mostly around trying to make the internet very robust. And there's a section at the end where Clark talks about what he calls design aids. So this is sort of everything we might consider formal verification, as well as maybe some software engineering kinds of tools. And he doesn't exactly sort of reject the use of formal verification, but he points out that they may be limited in how effective they can be at solving the kinds of problems that arise in a network. So he says, while tools to verify logical correctness are useful, both at the specification and implementation stage, they do not help with the severe problems that often arise related to performance. So he was worried about the kinds of things that can happen in a network where you have congestion, and that causes some piece of the network to be unavailable, and even if the network sort of satisfies its spec, it may not be a very useful network if it doesn't actually carry traffic. This sort of attitude has propagated to the current day. And I've heard people make the claim that the internet is this thing that we can't possibly understand. It's way too complicated. The kind of dynamics of the system aren't really things that a human can understand or we can even model. This is a quote from Danny Hillis. He's a sort of futurist who kind of warns against the dangers of building very complex systems that we rely on in every part of our life. And he says, our technology has gotten so complicated we don't understand them. Take the internet, we understand pieces of it. Like we can understand maybe how a single router works, but we don't really understand in detail their emerging behaviors. And it's perfectly capable for the internet to do something that nobody in the world can figure out why it did it or how it did it. And in the same interview, these quotes are from an interview with Hillis and Bill Joy, probably most of you know. Bill actually is a little bit more of an optimist, I think, and says the real problem with these kinds of systems is not that they're kind of unknowable, but that we've built them out of pieces that where we haven't been careful about defining their behavior carefully. So he points to systems, say, built in C, and says, if you think about things like undefined behavior, these systems often don't actually have a semantics. In a very deep sense, the programs written in C don't have a meaning. What it has is just whatever happens. And this kind of thinking, I think, is, probably everyone in the room is kind of feeling uncomfortable with these kinds of sentiments. But they're sort of the mainstream way that a lot of people think about systems and networks, that the kind of careful modeling and rigorous reasoning that the POPL community does is not a good fit for networks. So I want to claim that while there's truth in these views, that sort of the time is now to actually apply the PEPM POPL toolkit to systems like networks. And I think a few things have changed that make this the right time to do this. So one is that networks have just gotten really big. The original ARPANET, the predecessor of the internet, started out with really a handful of nodes. It sort of grew in universities and government labs, and didn't really explode until the sort of commercial age of the internet. And then there was sort of a second phase of growth around the 2000s with things like large data centers. And nowadays, even a network that's wholly controlled by one organization, like a big cloud provider, is sufficiently large that we need tools to help us understand their behavior. Managing these large networks has become sufficiently painful, and people make mistakes that we just can't keep going with sort of human scale processes. At the same time, these networks are expected to do more and more. So the internet, just implements some kind of best effort packet delivery, But nowadays, networks are involved with defending against denial of service attacks, implementing various access control and firewalls. They do load balancing. They make cache content. And for those kinds of networks to behave correctly, they need to do all of those things in addition to sort of providing basic communication. So the stakes have kind of gotten higher in two different dimensions. Another thing that's really an opportunity is that the architectures that we use to build networks are changing rapidly, and really only in the last 10 years. I don't have slides to show this, but some of you may have seen talks from me before where I sort of show pictures of what a computer looked like in the 1960s versus today. So the 60s computer looked like a big refrigerator, and today, my phone has more power than those computers. Well, in networking, the early routers were sort of these mainframe refrigerator-like things, completely vertically integrated, proprietary, kind of complex and black box. And still today, if you go buy a router from a company like a Cisco, it's the same kind of closed refrigerator kind of device. So that has started to change as people have started to say, wait, this is kind of crazy. Why do we build general purpose computers and routers so differently? And they've started to open up these architectures and try to do things like figure out, well, what is the right architecture for expressing packet processing that is that's very efficient and cost effective? And how should we think about the control structures of the network? And can we standardize the languages that describe the programs operating at those different levels? So there's been, the kind of buzzwords are software-defined networking has sort of proposed splitting apart the two pieces of a network, which I'll show in a couple slides, into separate pieces we can understand. And there's a more recent and active conversation around what I'll call programmable data planes. So routers that you can actually, that don't just implement maybe a handful of IETF internet standards, but where you can actually program them to process, basically writing a function from bits to bits. So they just process packets. They have state. They implement some program, just like a C program. And then, of course, the third thing is that our community and adjacent communities like the automated verification and so on have made tremendous advances. So we now have sophisticated techniques, operational semantics, denotational, better understanding of denotational approaches, various forms of logical reasoning that we're applying to increasingly complex systems. And there's also a lot of standardized tools now, maybe most prominently SAT and SMT solvers, that have gotten really powerful, and so we can kind of throw them at hard problems, and they do quite well. So I think all these pieces suggest that this is a domain where we could start to do things a bit differently. So what would we gain if we could kind of apply this POPL PEPM toolkit to networking? So one kind of obvious thing, and the thing that a lot of people sort of motivate their talks on this with is, well, we could find faults in configurations. Ultimately, networks are programmed by humans. They make mistakes. And if you have simple verification or testing or bug finding tools, you can often identify those errors before they get pushed out. Another thing that's a little bit subtle, but I think is actually quite powerful, network operators today, the folks who are charged with actually running networks, are extremely conservative because they've had no effective abstraction and no tool support. I often tell a story. The first time I visited Microsoft Research, I said, oh, can I talk to your networking folks? And I somehow got a meeting with the person who runs the core network at Microsoft. So this is not, say, the Azure data center network or even the network for, say, Microsoft Research itself. This is the network that sits between all Microsoft sites worldwide and has to sort of implement the internal corporate network. And he described a system where there were sort of decades of accreted policy and databases and Perl scripts that were together somehow generating the configurations of the network. And he said, there's a lot of stuff here I don't understand. Like there's various entries in my database that someone 10 years ago stuck there. And I'm afraid that if I take them out, then I might cut off Xbox or cut off Office Live or something. And so I just leave it alone. I don't know what it does, but if I touch it, it might change. And so if we had a better understanding of network behavior, we might be able to think about making more rapid changes to the network configurations, and that might help us provide better service, be more efficient, lots of things. And then a third thing is that network programs today tend to be really intimately tied to specific kinds of target devices. There's a lot of lock-in that happens where both in terms of the basic functionality and of course in terms of performance, unlike the programs we all run on our laptops, which you can basically switch from even one processor to another without too much pain in most cases. In networking, these things are really tied to the details of the underlying devices. So if we had all these, the ability to model and reason about network programs, we could make progress in all three of these areas. So what I want to tell you about is basically convince you that this is a great time to work on formal verification for networks. And I'll start with a little bit of a kind of primer on just basics of networking. And then I'll tell you about some of the work we've done on verifying the code that runs on a single node in a network, looking at very detailed properties. And then slightly shorter at the end, I'll talk about some work we've done on scaling this up to networks of multiple devices and properties that are richer in another dimension. And I'll close with some brief thoughts on future directions. Okay, so let me establish some basic terminology. I've already used some of this, but in case you've forgotten everything from your undergrad networking class. Classically, networks get sort of separated into a few different planes. Plane sort of refers to a layer of the software and hardware that implements the network. So at the bottom, we have the data or forwarding plane, which is basically responsible for actually processing the packets in the network. So it does things like forward packets on the next hop towards the destination, and it might also do some slightly more complicated computations, like if there's multiple paths, it might be balancing incoming traffic flows over those paths. Or it might do some kind of fast failover logic so that if there's a set of next hops and one of them happens to be down, it will seamlessly and sort of invisibly switch over to another path without any interruption. And it also implements some simple form of sort of queries, keeping track of utilization across devices, ports, different traffic classes, and so on. So the thing you should think about here is this is sort of, on the one hand, fundamental. This is sort of ground truth for like what actually happens in the network, how are packets being forwarded. But it's also important that this be really fast. One could actually debate this. You could ask if networks really need to provide such tight performance bounds. But at least today, most people think about these devices as being, I've got a 48-port 10-gig switch. So I can basically, take my switch and hammer it with traffic at every port can be receiving traffic at 10 gigs, and I can route those incoming 10 gigs flows over any of my other ports, and the device will sustain that line rate. So it would be very hard to achieve that if you had a server with a bunch of network cards stuck into it and a bunch of cores. You'd need a lot of cores to keep up with that kind of rate. And so these things tend to be designed to be computationally restricted so that you can get predictable and high performance. So we're not going to be able to implement application logic, at least not all of an application, on one of these things. So the other piece of the network, of course, is the control plane. Traditionally, the control plane would actually be bundled with a data plane in each device. So if you buy a router, it has both a control plane and a data plane. The main idea in SDN was actually to separate the control plane, park it off somewhere else, and let a single control plane manage a collection of these data planes. And the control plane is more like a general purpose computation. So it does things like discover or learn the topology of the network. It'll build some graph representation of this. And then it will use algorithms like Dijkstra's algorithm or Bellman-Ford or others to compute paths between the endpoints through this graph. And it will also enforce things like policies. If you have some kind of access control rules for your network or isolation policies, it will implement those. If you make dynamic changes to the network, like you propagate a new policy, it's responsible for figuring out how to distribute that onto all the devices in the network. So that's the control plane. Let me tell you a little bit more detail what these things look like. So in software-defined networking, the data plane can be thought of as some kind of program whose main sort of primitive are match action tables, basically lookup tables. So we can look up values from the packet, maybe the IP address, and then we can take one of several predetermined sort of procedures or actions that do things like drop the packet or forward it or divert it to the controller. And then the control plane, it has a slightly richer API. So it's not actually involved with processing packets, at least not in the normal case. But it has some kind of API. This is one particular API that was proposed, but it has an API for learning about network events like switches joining or leaving the network, maybe ports whose status goes from up to down or down to up. Maybe it can read some of the state that might be maintained on these devices. And then it can control the data planes by manipulating the entries in these match action tables. It can also do some limited forms of injecting traffic into the network and requesting state, like what rules are installed, how many packets have hit a certain rule, and so on. So this is the SDN control plane. And what I want you to kind of realize is that this kind of architecture enables, or is most commonly implemented as a form of partial evaluation. This is sort of a cartoon version of a very famous talk by Scott Schenker at Berkeley, who sort of proposed this SDN model as sort of the right way to think about networking. So the way to think about it is that there's a control loop here. So stuff is happening down in the data plane. Packets are coming and going. Switches are entering and leaving. Links are changing their state. And some of these events trigger a call to the control plane saying, hey, something happened. And the control plane then runs a general purpose program, maybe in Java or Haskell or whatever you want, and it then responds with some of these control directives. So there's this control loop. And what most SDN controllers actually let you do is write a very sophisticated and general purpose program, again, in Java or Haskell, and then they maintain some special data structures, like typically the topology. And what happens is, when the topology changes, they specialize the network-wide program to this topology to compute sort of a specialized or residual program, and then that gets converted into modifications to the flow tables. So I've seen a few papers that actually try to take this idea of sort of specialization and things from the PEPM community literally. We had a paper at POPL 12 that proposed a technique called reactive specialization, and there's some work out of Brown from Tim Nelson and Sriram Krishnamurthy and others that also looks at how you might have a more unified tierless abstraction for programming this, and they use similar techniques. But hopefully this kind of whets your appetite and gets you thinking that this could be an interesting space to play in. Okay, so what I want to do now is dive in, and I'm not going to actually talk very much about the control plane until the end. So you should imagine that sort of this upstairs part of this picture is frozen. And for the rest of this talk, the goal is to be able to model and automatically reason about behaviors at the low level. So in the first part, I'm going to tell you about a tool called P4V that we built a couple years ago and published at SIGCOMM 18. The contribution to this work was really to show that modern sort of program verification and formal methods can be applied to the kinds of programs that run on real routers, and they can scale up to large programs and answer interesting properties. So let me tell you a little bit about the traditional way that these refrigerator-like boxes like this Cisco router get validated. If you are the person responsible for managing a network at a large company, your typical way of sort of bringing new gear on board is you would figure out your requirements, put out some bid, some vendors would come back and make offers, you'd buy some of these things, and then the shipping crate arrives, you unpack it, and you're like, great, I've got this router that can do all these protocols and has this much memory and can sustain this line rate. But you'd sort of be a fool to just plug it into your network because, especially if this is maybe a first generation device, I mean, who knows if it actually does what the vendor says it would do. So there's a whole nother industry around testing. This is a box you can buy from a company called Keysight whose sole purpose is to sort of generate lots of random inputs and make observations about what's happening. So one of these wires would sort of generate inputs, and then you'd configure this thing to send them back to the box, and you'd sort of do not exhaustive, but quite extensive testing of the box. And this is hugely expensive. I mean, this box is $100,000 or more. Of course, it takes time to actually run these things. You need engineers who are trained in running them. But In a traditional network, once you buy this thing and deploy it, it's just going to sit there and run more or less for like 5 to 7 years. So these high costs of testing are kind of amortized, and it's not too bad. But one thing that's been happening in the last 5 or so years is companies like Barefoot, which I worked at during my sabbatical and still consult for, are developing new chips for the insides of these routers that don't just implement standard protocols, but can actually be programmed by ordinary developers. So you can buy switches today, not yet a big beefy router, but switches for maybe a data center or even some routers that have this kind of chip inside. And you can use a domain-specific language called P4, which I'll tell you a bit about in a little bit, to actually change at the sort of bit level how this thing processes packets. So there's lots of reasons this is a good idea. I mean, one reason is just figuring out what the right hardware designs and low-level abstractions for packet processing is a thing that I think is long overdue. But in terms of immediate benefits, Barefoot's customers are finding that being able to customize their routers to do just what they want is very useful. Often there's a new feature they need, and instead of waiting for a vendor to implement it and come back to them, they can just write a different program. And there's even a community that's sort of looking at extremely exotic or novel uses of the network. Things like actually relocating some of the application protocols onto the state and computation you have on routers. So implementing things like Paxos on a router. So this is kind of cool and exciting, but that traditional approach to validation based on testing clearly is not going to scale. If the behavior of a router is changing at sort of software timescales, you might have weekly or even daily changes to your router code, and you're not going to take it offline and go take a testing appliance to make sure it's doing what you want. So the insight, of course, which is obvious to everyone in this room but is not obvious to networking folks, is, well, since we have a description of what this thing is supposed to do, we could use language-based analysis techniques to check for correctness properties. So sometimes I have time for a demo. I think I won't have time today, but if folks want to see a demo, I'd be happy to show you one during the rest of the week sometime or later today. This is kind of a not quite 50,000, maybe 10,000 foot view of a P4 program. I'm not going to pronounce every piece, but let me just kind of give you a tour of kind of what the language speaks about. So first, P4 doesn't bake in any traditional protocols at all. So you have to start by defining types for all of the different packet formats that your router is going to process. So you can see here, if you're reading carefully, I've got types for the Ethernet header and for the IPv4 header. This one, you'll notice I've even written in a non-standard way. That's fine. I've sort of taken the first 64 bits and just glommed them together into one field because I don't need them for this program. And then you write some parsers in a little state machine language that goes from a serialized representation of the packet into populated instances of these types. Then we have sort of the main part of the program. So the parser always runs at the beginning. And then the main part of the program is actually down here in something called a control. This is shorthand for control flow. And essentially the control strings together one or more, well, 0 or more of these match action tables. But the match action tables can be customized to your program. So you can define what the keys that are matched in the table will be, and you can also define what actions can be applied in each table. And an action is basically just a little snippet of imperative code that manipulates the state in the headers and maybe invokes some other external objects or other built-ins, and that's it. So how does this work? Well, a P4 program is not really tied to any particular kind of device, but if you're using it to program a router, your router probably has a hardware design that looks like this. This is what Barefoot's chip kind of looks like abstractly, and it's also what sort of the last many generations of router chips, even for conventional protocols, have looked like. So as I said, these data planes have to be fast. So this thing is going to be a feed-forward hardware pipeline. There's no possibility of looping or stalling on the normal path through this thing. And basically, packets come in, they get parsed, then there's some memories and arithmetic units that manipulate the bits that have been parsed. In the middle, there's something called the traffic manager, which can do things like drop the packet or make copies of the packet, schedule the packet if we're doing some kind of queuing. And then after we've made the decision about how the packet should be forwarded, we can do some further processing of the sort of scheduled and forwarded packets. And then finally, at the end, we deparse them back into a serialized representation, and they go out. OK, so P4 is, I think, a fairly actually high-level language compared to what the hardware has. Oh, I should say one more thing, which is this is not the only design, of course. You can implement P4 programs in the Linux kernel. You could implement them on an FPGA. You could even imagine an implementation that used a whole bunch of CPUs and some kind of clever memory substructure to implement the same semantics. This is just the one that kind of looks most like a router chip. But of course, the language has an independent semantics. OK, so P4 is fairly high level, and it kind of abstracts over all these different hardware designs. But it's still kind of low level in the sense it's kind of similar to C. And there's a bunch of gotchas that can arise when you write programs. So let me take you through a few of these. So here's the same example I showed you before, kind of stripped down to a slightly smaller subset, just to kind of get at the essence of some of these errors. So here, I've got a single table, ACL for access control list. And what it does is it reads the parsed IPv4 destination address. It uses a prefix match, so you can have multiple matches that get, and this says how to disambiguate if you have multiple rules that match the given packet. And then we can either allow, which basically forwards the packet out a certain port, or deny, which just calls a primitive called drop, which will cause the packet to be dropped. And that's it. So this seems very simple. What could possibly go wrong? Well, there are some faults that could happen here, but I want to jump to a slightly more complicated example. So let's suppose that we take this example and we add a simple form of tunneling. Let me quickly explain what tunneling is used for. So if your network, maybe your home network or your university or your company, buys service from another, maybe internet service provider, to carry your traffic over to some other location. Perhaps you have an office in another part of your country. Typically, that internet service provider, they have their own network to manage between your two sites, and yet they want to kind of make it appear as if there's just a wire going between the gateway at your one office and the gateway at the other side. And so to do this, what they'll do is basically tunnel your packets through another layer of headers that they use to carry the traffic through their network while preserving all the bits in your packet. And so 4 and 6 tunneling here means that at the point where this program executes, the packet actually has sort of 2 IP headers inside. One is an IP version 4 header. This is the current IP version that is most widely used. But the topmost IP header is actually an IPv6 header. This is the, of course, emerging revision of IP that's taken a long time to get out there. So you can imagine that this is the thing that you're using in your network, and this is what your ISP is using. And the goal of this program is at the end of, at sort of the termination point, we'd like to get back to the original packet that you transmitted at the other side. So this is the kind of final termination of this tunnel. And what we want to do is take this inner IPv4 header, and raise it up to the top level. So here's some P4 code that does it. We do it in 2 pieces. So the first piece is that we basically use this tunnel decap table to invoke a procedure called decap 4 and 6, which copies this header, inner IPv4, to another variable, just regular IPv4, and it removes this. So I haven't shown the other IPv4 header, but basically there's another instance of IPv4, and we just want to copy these bits here. So at this point, we have this kind of funny representation. We have a packet that has Ethernet, which is the lowest level header, and then we have both IPv4 and IPv6. And so to get back to a well-formatted packet, what we're going to do is call this other table, which terminates the tunnel, by removing the IPv6 header, and then also updating the ether type field. Ether type is a kind of type field that's in the lowest level header that signals what kind of header comes next. So, so in 2 steps, we basically propagate this inner IPv4 header up and then reset the top level structure so that we have a well-formatted packet again. Now, why do it in 2 steps? We could do it in 1 step, and that would not have the bug I'm going to show you. But there are other reasons that people want to structure the code this way. So this is actually an example taken from a real switch program. OK, so the problem here arises in this middle state of our program. We've got this. We've got a collection of parsed headers. We've got the Ethernet header, which is always there, but then we have both IPv4 and IPv6. So no packets on a legitimate network would have both of these things. And if you sent this data to most devices, they'd get very confused. It's worse because I actually lied a little bit when I told you about the abstract hardware model that's used to forward packets in P4, at least for router chips. So I said that basically, there's this traffic manager that does things like drop packets and schedule them. And I sort of implied that all the data that's sort of live in your program here just gets carried over here, provided the packet's not dropped. Well, actually, what happens is the packet gets serialized before this traffic manager runs. So there's a deparser that runs here and takes all of our parsed, nicely typed state and puts it back into a bit string. And then after we've queued it, dropped it, cloned it, whatever, then we reparse it at the other end. And I also lied because there are actually some cycles in this graph. So there's the possibility of looping back. And so in practice, you want this deparser and this deparser to be the same, and you want this parser and this parser to be the same. So now maybe some of you are starting to see there might be a problem here. We've got, and it's very much like a bidirectional programming problem, we've got sort of a set of packet formats that at different places in our program we want to handle. We've got a separate serializer and deserializer that are supposed to handle that format. And then we've got this kind of C-like program that's being mapped down onto this architecture. And so if the first of our transformations, the I think it was decap 4 and 6, the first one that just moved inner IP4 up, gets put here, and then we deserialize the packet and then parse it again, and then we do the termination action here. So in other words, between these 2 phases, we do the deserialize and serialize. What will happen is we'll deparse this weird state. It's actually not well specified necessarily which of these 2 things will happen from what I've told you. But let's suppose that the IPv4 header gets deserialized first. So now we have a bit string that looks like this. And now it should be clear if we try to parse this. I haven't told you exactly how the parser works, but the parser sees an Ethernet header first, and then it says, OK, the ether type is IPv6. It's going to start parsing these bits as the IPv6 header. So we'll basically parse the wrong bits and end up flipping or scrambling or screwing up the bits in our 2 headers. And now when we do that termination action, everything has gone wrong. We've just got garbage. So one important property that you need to hold if you want to reason about correctness, we call it reparsability. And that's that the kind of simple view of this router chip, that state sort of gets carried over as you go across the TM, actually does hold. And in the interest of time, I'll just sort of list off. There's a whole bunch of these properties. This is just one property that happens to be kind of particularly difficult for programmers to keep in their head. But there's lots of other properties that you might want, both of kind of the particular architectures that are used to implement P4 programs. I didn't mention this, but P4 actually has some of the mistakes that languages like C and Java have made. So they're sort of the equivalent of the null problem in P4. And then, of course, there's program-specific properties you might like to hold, like if you claim that this router implements some IETF standard, it might be nice to check that you haven't actually messed up the logic of that protocol. So again, I've sort of tipped my hands. With our technique for doing this is to build a program verification tool where all of these things can be formalized in logic, and then we can check them against the source code of the P4 program. And I don't want to claim this is a completely straightforward exercise, because there's actually a number of challenges that make it a little bit more complicated than it might seem. So one challenge is P4 is a language designed by an industry consortium, and the language specification doesn't actually have precise formal semantics. There's a 150 or 200 page English document. It's got some pseudocode, it's got some kind of quasi-math, but it's not something like the standard definition of ML or the kinds of things you see with WebAssembly or in most POPL papers. So in order to reason about P4 programs, we need a semantics. And so we followed the approach that Arjun Guha and Shriram Krishnamurthy used in their JavaScript work, and defined a simple core language. We used Dijkstra's guarded command language, and defined a translator from the surface syntax of P4 into this GCL. And also, like Guha and Krishnamurthy's work on JavaScript, we were concerned that even though we're smart people who can read specifications carefully, we might have gotten some things in our translation wrong. So we also wrote a little symbolic executor and generated a whole bunch of input-output tests for the P4 programs that are included in the P4 compiler suite, and tested it against several of the existing implementations of P4. In particular, the Tofino, the model of Barefoot's Tofino chip that's used for simulation internally. And so we just did differential testing to see, is our semantics capturing the same behavior as what the chip and compiler are realizing? And we found a bunch of discrepancies, and actually some of these got upstream back to the spec, making it more clear what was intended. Okay. A second challenge is that a P4 program describes this, at a very low level of abstraction, how packets get processed, but it doesn't actually tell you what goes into the tables. So if you go back to this original access control table I showed you, at runtime, this table will have entries in it. It will have specific matches and specific actions. And this thing we can reason about, because it's very clear what should happen. But without knowing what this is, it's hard to say what will happen after we execute this table. So one thing you could do is, since we're in Dijkstra's GCL language, you could just use, this is our notation for choice, you could just say, well, when I hit a table, I don't know what happens. I could run any of the actions, or I could miss in the table, of course, if there's no matching rule. And that's the behavior of the program. So this is a syntax for a non-deterministic sort of choice of any of the actions or miss in the table. And this would be sound, but of course, it may give us sort of, not mathematically, but pragmatically sort of false positives in terms of violations of our properties. Because control planes are often carefully programmed. So in particular, there can be tables, maybe even pairs of tables, that are programmed together by the control plane. And if you simply sort of assume that any table can do anything, you won't capture those kinds of dependencies between tables. There's other interesting dependencies that control plane programmers worry about. From a pragmatic perspective, if you just sort of did this and started reporting lots of bugs to developers, they'd sort of tell you, go away and come back when you can model the kinds of constraints that I have in my head. So we need some way to model out to rule out these false positives. We didn't do anything super creative or brilliant here. We just sort of did the obvious move, which is to model the interface between the control plane and the data plane using a little DSL that really just is sugar for kind of first-order logic assertions that allows us to constrain the choices made in the tables. So for example, for our tunneling example, it would be very natural to assume that if you hit in one table, you hit in the other table. So it's not possible to only do one of these actions. And we can model that by this kind of symbolic control plane that says, basically, if the action we ran in the first table was this, then we ran this action in the other table. Okay, another challenge that's, again, sort of a pragmatic challenge is probably everyone in this room loves writing formal specifications, but unfortunately, most programmers do not. And so we were very worried that if we started out with a tool that felt like theorem proving, that we would not get any adoption by customers or even engineers within companies like Barefoot. So we put quite a bit of effort into lowering the annotation burden by coming up with a bunch of standard safety properties that you sort of want every program to satisfy, and also making even the annotations you might add not look like logic. And then the third challenge is just scaling up. In doing this work, I actually had not really studied program verification beyond the sort of undergrad level in detail, and went back and read a lot of the older papers, say from people like Cormac Flanagan and Rustin Leno and Todd Milstein and so on, when they were doing their work on things like ESC Java. Also looked at a lot of the work out of Microsoft and modern work on things like separation logic. And a lot of this work, rightly so, starts from saying, well, we need verification to be compositional. That's how we're going to make it tractable, to write down all the annotations we need and also make it scale. And again, because we didn't want programmers to have to do any extra work, we wanted to see how far we could push with just monolithic verification. Our hypothesis was that, well, these P4 programs can be kind of big, like 10,000 lines of code, but they're kind of simple because P4 doesn't have things like pointers, doesn't really have complicated concurrency, it doesn't have loops. The loops can all be unrolled. So, given how good SMT solvers are, maybe we can just, throw all this at an SMT solver and make it work. And I'll say some engineering is needed. So using some of the insights from the work that I described are needed. And we do some optimizations in our front end to try to shrink down the size of the program. And some of these are actually important to make the tool scale. But I would say overall our experience is positive that one can get by for these kinds of programs without having to do compositional verification. Okay, so what does this look like? Well, this is kind of the picture you're obligated to have in a program verification talk. So we start with our P4 program. We provide this control plane interface. And then we take it through a fairly standard pipeline, just generating verification conditions, feed it off to an SMT solver, and get either success or a nice trace telling us where in the program we went wrong. This is a snippet from our evaluation. So just to show you that it works pretty well. So here we took a bunch of open source programs, also a bunch of customer programs at Barefoot. Most of the customer programs are implementing either kind of a traditional data center switch or router, or a subset of features found in a data center switch or router. And we were quite happy that basically all of them finished in sort of, with a couple exceptions, around a minute or less, both with and without a control plane interface. There was one program in our benchmark suite that Z3 ran out of memory for. This is kind of a weird, I don't know if it's weird. This is a interesting research project trying to do virtualization at the P4 level. So it has a very kind of large blow up. It's trying to simulate the bit level behavior of a P4 program in another P4 program. And Z3 kind of choked on that. But all the others, again, without too much engineering, we were able to make work. And I should have said one property we're checking here is a cross-cutting safety property, basically that every bit in the program is well-defined, so there's no undefined behavior. And you might wonder, well, how costly was the control plane interface we had to write? Here it is, so it's not trivial. This is for a program that was about 6,000 lines of code originally. So the control plane interface ended up being less than 1,000 lines of code. And most of these are assumptions about single tables, and there are a few assumptions about groups of tables. We've kind of classified them here. It took me and Jed Liu about 2 days to do this, just working interactively with the tool. So we basically would run the tool, get a counterexample, go back and look at if that counterexample was genuine, if it was a bug, or if there was some reason it couldn't happen. Sometimes we go talk to the team that was writing the control plane. They would tell us why that condition couldn't happen, and then we write down a condition that captured that. And we did find about 10 bugs in doing this. Okay, so that's what I'll say about P4. I think I have about 5 minutes left before questions. So I want to briefly talk about, just give you a taste of some other work that we've done, which is sort of attacking the same problem, but at a much higher level of abstraction. And again, what I want you to think about is, mathematical tools for modeling the behavior of these data planes, either richer behaviors or richer properties that we might eventually use as a piece in a control loop that we could verify, end-to-end behaviors for. A natural question to ask is, could you take everything we've done with P4V and then scale it up not just to a single device, but to a network of devices? And a flippant answer is yes. I mean, this is what a lot of work on network verification has been doing lately. So if you've heard of tools like Netcat or header space analysis or Veriflow, all of these tools are basically doing just this. So they're building some kind of model of the network topology and the configuration of all the data planes in that topology. And then they'll take a property like maybe, they'll take the network and its config, and they'll take a property like, the property is here. Are my packets going to be delivered to my destination? And you can feed this in and get a yes-no answer actually reasonably quickly. But a natural question to ask is, well, what happens if there's failures? And unfortunately, if you have one of these deterministic verification tools and you add to your model maybe some kind of random failures, like maybe links fail independently with probability 1%, in a lot of topologies and for a lot of configurations like shortest path routing, the tool will come back and say, well, maybe. And so what we wanted to do was to have a way to reason quantitatively about these kinds of properties. So not just get maybe, but maybe get a precise answer, like in this topology, since the two links can each fail with probability 1% and it's independent, that the probability of getting from left to right in this topology is 98.01%. Going even further, it turns out that you can model a form of fast failover, where the data plane actually detects failures and then routes around them with either randomly selected or pre-provisioned backup paths. And so if we enrich our behavior to do that kind of detour, here I'm using random failover to some other next hop, and if we bound the failure model, maybe assuming that at most two links will fail at any moment in time, now we want to be able to show that, well, actually, this thing will be resilient. And this is a kind of reasoning that at least designers of, say, data center networks are starting to do. So why is this challenging? Well, the scenario I described here, it's kind of simple to describe, but it's quite subtle, actually, because the set of paths that can fail can change at every moment in time. So I bounded it to be 2, which will cause me not to ever be disconnected, but it could take me a very long time to walk through this network and get to my destination. In particular, when I'm right here, the packet could go up, and if I go up, the only way is to go back to the source, because I'm taking a random choice. And so I might cycle around this, making random choices for a long time until I eventually make the right choice to go down and get to the destination. And yet, I want to be able to show that I will deliver the packet with probability 1. And the reason, of course, is that this infinite loop has probability 0, because every time that I choose to go around the loop, I'm multiplying together the probabilities of each of these choices, and so it eventually goes to 0. And so to do this, you need a semantics for these network programs that's quite different from what I showed you for P4V. So instead of modeling these things as kind of functions on some state space, we now need to model them as random functions. And the key insight that behind this work, which was published at PLDI last June, is that actually the domain is still simple enough that you can model these kinds of random functions used in packet processing as Markov chains. It has a very large state space, but we can actually model that state space quite symbolically. In the tool that we built, we kind of took a source language that has this kind of random choice in it. You can also sort of input arbitrary other distributions. We have a symbolic IR based on some structures called forwarding decision diagrams augmented with probabilistic choices. And then we have a backend that actually converts this into a sparse linear algebra representation that we can pass off to a solver to find the limiting behavior of the transition matrix represented here. So again, I'm obviously going fast through this. You can see our PLDI paper if you want to see the details. But the kind of thing I want you to take away is that you can actually go beyond these simple functions and start to reason about probabilistic behavior. And that can both be made fast, and it has some interesting applications. So in particular, one of the things that's in our PLDI paper is we did a case study of a data center design out of the University of Washington from a few years ago called F10 that proposed some tweaks to the kind of multi-rooted trees that are used in data centers to enable better fast failover behavior and lower length paths when you see failures. I'm short on time, so I won't explain the details, but it's a kind of tree topology. And we actually implemented the routing scheme that they proposed as a series of refinements. So we started with kind of shortest path routing with no failover. Then we took failover that used at most 3-hop longer paths. And then we implemented the full algorithm that was in their paper. We call it F10-3-5 because it has a combination of 3-hop paths and 5-hop paths. Turns out that this requires a little bit of state in packets. You have to keep track of whether you tried a 3-hop path or not, but you can fold this into the representation that our tool uses without actually having state on the routers. And we verified that, that these designs actually provide the stated level of resilience. So if you bound the number of failures here on the left, and you take these schemes, first you can see that the shortest hop scheme doesn't do very well as soon as there's a failure. The 3-hop scheme kind of behaves as you expect. And that's a bug. We actually screwed up our implementation originally. We had this extra state to keep track of the 3-hop and 5-hop paths, and we forgot to initialize it when we first encoded the program, and so our tool told us this thing never delivered packets. So that kind of actually gave us some confidence that our tool was doing something right once we found the bug. Once we fixed the bug, then it went up to 3-hop paths as well. And you can do a little bit more besides just kind of verifying this kind of resilience properties. You can actually get a quantitative representation of the distribution of behaviors you'll see, and you can do various statistics like look at what's the probability of delivery as the link failures scale up. I'm quite short on time, so I won't explain this graph in detail, but essentially the more sophisticated schemes are doing better. Okay, so I want to very quickly just highlight a few areas that I think the PEPM community would be interested in, could be interested in looking at. So one thing is that obviously I haven't talked at all about the control plane other than to say what it is. And of course it's useful to have a bunch of tools for modeling data plane behavior, but the kind of holy grail would be to be able to model the control plane as well. And there's a few different things you could do. You could think about modeling traditional control planes like BGP, and people like Ryan Beckett at Microsoft and Dave Walker and Todd Milstein have been doing that in work like Propane and Minesweeper. You could also smush these together in the kind of tierless approach, and I looked at that in a couple of application-focused examples. So we've taken a control plane that does a bit more, in this case caching of key values, and actually smushed it together into a P4-based implementation that partitions the behavior between the control plane and the data plane. So that's another way that you could push this a little forward. And then there's also some other kind of basic primitives that I think we're sort of just starting to understand. So of course, I said that concurrency was not very complicated in existing models. It's very natural to want to add mutable state on the routers. That's a thing that routers can do. But now you have a complicated concurrency problem. There's some preliminary initial proposals, but I think they haven't quite nailed the problem. And then another area, getting all the way back to Clark's original kind of comment about verification, reasoning about performance, not just in terms of reliability, but in terms of things like scheduling and bounding queue lengths and service level agreements, is another area where we're starting to see programmable schedulers, and it would be great to extend formal verification to also talk about maybe bounds on performance as well. Okay, so I'm running short on time, but I hope I've convinced you that this is a rich area to explore. It's a lot of fun, I can say, if you like hacking on systems. There's a lot of classic problems that I think have been reopened by this fresh perspective, and also new problems that are emerging. And I'm most excited because it's a rare chance to kind of rethink the foundations of networking really from the ground up and using the tools of our community. Okay, so I'll stop there and take a couple questions if there's time. Thanks.
P4 has a non-determinism there, and then you add control plan, right? And this code will be written by another guy or by the P4 guy. And also in the challenge part, we also mentioned about control plan. There are some traditional approach. What's the relationship among all of them? Yeah.
Yeah. So right now, the extra interface that you write, ideally, I think it would be written by the programmer of the data plane.
Right, right.
Maybe in conversation or consultation with the control plane designer. But I view this as really a part of the data plane. It's sort of all of the invariants about this non-determinism that are needed, or all the constraints in this non-determinism that are needed for the data plane program to satisfy its specification.
Right.
It's a bit of a shame that P4 doesn't right now have a notation for writing down these kinds of constraints. Some folks at Google are working on adding it. They're doing a bunch of testing mainly of their P4 programs, and they would like to be able to express the same kinds of constraints. So they proposed an extension where you could write down these kinds of constraints in the program. Okay. And then going back to the interface with traditional control planes, there's quite a gap. I mean, if you look at what kinds of things, say, BGP talks about, it's expressed in terms of autonomous systems and prefixes and things called meds and communities and all these acronyms. It's quite a different view of behavior than this. I don't think it's insurmountable to, much like a compiler, much like WebAssembly or JavaScript looks very different from x86. Right. I think you could get down by careful understanding of the layers, but people just haven't done that work yet.
Right.
Maybe the closest is Propane, this work from Ryan and Dave, that tries to extend a kind of netcat-like syntax and semantics with some features to model the kinds of choices that are made in BGP.
Right, right. Okay, thank you. So any other questions? Yeah.
So if you would like to summarize, what do you think would be the main differences in verifying SDN programs with respect to classical, distributed components or cloud computing or these kind of things?
So a few different things. So first, for data plane verification, I think things are just simpler. So a lot of the complications that you have thinking about a single program, say in C, you don't have to deal with in a language like P4. No pointers, really simple data types, and only very limited loops. So really, elementary undergrad program verification can be applied to this. Once you get to multiple nodes, now you have interactions between packets or flows coming across different devices, and depending on how much of the behavior you're modeling. So if you're modeling queuing, for example, now you need to model the interactions between different flows going across a shared queue, and that gets very complicated. If you are modeling just reachability, then perhaps the problem becomes a bit simpler because these interactions don't actually affect each other, so you can decompose the problem that way. So I guess I can say more, but let me just try to summarize quickly. I think what excites me about this is that there are both kind of restrictions you can make that make some problems that are hard in the general purpose case really easy, and you're able to scale them out a bit more in this case. But there's also this richness of having a distributed system and concurrency and so on that makes it not completely trivial.
Any more questions?
This is probably related to Zhenjiang's question. Seems you are saying that currently all the P4 programs are handwritten. There's no high-level language that you can use to write at the high level and translate it to P4.
I'm not aware of anyone who's writing a compiler that uses P4 as an intermediate language. One reason is that a lot of people in networking think that P4 is too high level because it leaves, abstracts too much. Yeah, maybe the only exception, I do know a couple of people who have built tools for kind of generating P4 from sort of slightly richer templates, slightly richer data types, or they want to write down loops, so they write a sort of macro expander. I think it would be very interesting to take a richer language, maybe one that's avoids some of the missteps of P4 and either compile it to P4 or just propose it as a replacement. And there's lots of things that such a language could have. It could have a better data model. It could have more sane semantics for the state. It could have, more powerful constructs like loops and other control flow that maybe gets compiled away. So I think there's a space for that kind of language as well.
Okay, any more questions? No? Let's thank you.
Okay,
Thank you.
thank you.
Okay, we have a short break.